Good morning. I'm Zach. I am a master's student at Michigan, um, and I have some of my friends here with me. So I'll just introduce them really quickly.
I'm Chad. I'm an undergrad at U of M.
I'm Paul. I'm also an undergrad at U of M. And I'm Grant, also an undergrad at U of M. We're all mechanical engineers.
So we're happy to be here. I think I've done this for a couple years, so this is a really fun lesson. We have a cool zip line over there. I'm gonna make sure you guys can hear me. I like the angel shirts. My sister's a student teacher at Angel now, so she teaches second grade, so I don't think you guys probably would. Who is she? Yeah. Miss Star. Well, okay, that's fine. So today, have you guys all read about the zip line? You know what the project's about, basically? Yeah? Can anybody tell me? Sure? So we have all these different items that you guys can see over there. So basically what you'll do is you're going to hold it up here, go up those steps, and so once it breaks this photo gate, it's like a light sensor. So once it breaks the light, it's going to start the timer, and then it will stop. And we're going to learn about different ways to control the speed and really learn about why your carrier, the ping pong ball, is going to go down the zip line at different speeds. So anybody know what energy is? Let's see, yeah? Exactly. Yeah, what else? Yeah, exactly. Yeah? Right, exactly. Equals MC squared. Anybody know different kinds of energy? Yeah. Great. Any other kinds? That's potential. Good. Yeah. Any other? Anybody see really tall things in the ground that have big propellers? You know what that is? Yeah. Yeah. And so that's wind energy. Anything else? Yeah. Yeah. And I mean, there's a lot. I mean, we can keep going if you want. Yeah. Exactly. And you want to? Exactly. Yeah. Exactly. Hydropower. So yeah. So all these different kinds of energy. We only didn't say nuclear, but that's okay. So you don't need to know this. I'm just for your knowledge. But today, what are we going to focus on? What type of energy is in a zip line? Any of you guys know? There is friction. Anybody else? Yep. Exactly. So potential and kinetic are the two main forms of energy that we're going to focus on for the zip line. So let's see. Oh, sorry, you're clicking. I'll just do it. Okay. Um, cool. So this is potential energy. So think of potential energy as something that's stored. So can anybody tell me if I'm standing right here, okay? But then, and don't do this because this isn't safe. But then if I stand up here, which one has more potential energy? And yeah? Right, and why is that? Yeah? Right, so that's more about the conversion, but purely potential energy. So potential energy, think of it as a change of height. So when I step up here, if you can see, my height's increasing. So if you think about it, like if I were to fall from here, it's going to hurt a lot more than if I just fall from here, right? And even imagine if I was at the ceiling, that would hurt a lot more. So yeah, we don't want that to happen. So like we say here, what's scarier? If you're over your front porch or like, right, yeah. So it's really just the energy of anything that's in motion. Okay. So can anybody tell me? Has anybody play baseball? Ooh, we got some baseball players here. Okay. Um, what hurts more if somebody throws a fastball at you, or if they throw something underhand, a soft underhand? Yeah. Why? Right. And what else? What else does it have? Exactly. It has more kinetic energy. And why is that? Yeah. Exactly. And then what else? Does anybody know? There's one more thing that I want to get at through here. You guys have any idea? Okay, that's okay. Yep. Right. And there's one thing actually. So kinetic energy really depends on. So it depends on the mass, but it also depends. If the same baseball is the same, it weighs the same, right? It has the same mass. But it's also how fast it is, its speed, right? So the higher the speed, it's going to hurt a lot more. So it's going to have a lot more energy. So, what you guys were saying, you're all talking about potential kinetic. What is that called? Yep. Yeah, so it's a transfer of energy, the conservation of energy. So somebody was saying in the beginning, energy is can't be created or destroyed. Is that you? Good. Yep. So energy can't be created or destroyed, but it can be conserved. So what happens is, let's say you're throwing a baseball, right? You have all of the energy stored in your body. So it's the stored energy in your arm, and then it transfers to the baseball, and then it goes to purely kinetic energy. Okay, so we're gonna actually do some fun, cool demos. Actually, really quickly. So if you think about this car on the top of the hill, you need to give it energy, so now it has all potential, and then when it comes down, it has all kinetic, but you're changing it to be potential and then to kinetic energy. So it's a transfer of energy, the conservation of energy. So now we're going to do some demos. So I want you guys all to come up here. We're going to come around this table. You guys can take a seat on the ground if you want, or if you can't, you just. Okay, so let's see. Does this work? Okay. So, all right. Can you guys all hear us? Great. Keep it up. Just turn it. Okay, there we go. Because it's just that way it can be recorded. Okay, so does anybody know what these things are? Yeah. Uh-huh. And what is this? Yeah? It's not a pulley. It's a really confusing name. Yeah, they're pretty cool, aren't they? It's what? Do you have any guess? It is a pendulum, but it's actually called the trebuchet. Anybody heard of that? Oh, yeah, those were used back hundreds of years ago. But I guess people still use them today to throw pumpkins and stuff. You guys ever seen that? The pumpkin chunkin or something? Okay. So we're gonna have these guys come talk to you about how these conserve energy and how they transfer potential to kinetic. And so we'll also do some demos and it'll be pretty fun. So
So after just learning about conservation of energy, like Zach just ran over with you guys, how much energy do you think this catapult right here has right now? Yeah? Yeah, exactly. So it's not moving and nothing's really stored in it right now. Like it's not going to be able to throw anything, right? What about if I pull this back to right about there? What's its total energy look like now? Yeah? A lot. A lot of what? What kind of energy? You're right. You're on the right track. Yeah? Potential. So what do you guys think then will happen if I put this ball, and you guys should move to the side. What do you think will happen? Yeah, I don't know.
I don't know how accurate it can be.
I can be accurate.
There we go.
What do you think will happen when I let go? Yeah? Yeah, great. So all this potential energy stored in this string right here is going to be released, and it's going to go into the catapult, which is going to go into the ball, and it's going to hopefully fling it. There you go. So, yeah, it works pretty well.
Great. Awesome. Okay.
okay, great. So we now see how that transfers kinetic into or potential into kinetic energy, right? What about this? This one's confusing, isn't it? What's happening here? Yeah. Okay, and so What part of this has the potential energy? What are we doing with the weights to give them potential energy?
Pulling it back.
Okay, and so what does that do? What does it do with the weights? Yeah.
It makes the weights go up higher if they're more potential energy.
Right. So do
If you release it will go down and have more.
exactly. So do you guys remember? It was real quick, so maybe you don't. But potential energy increases when you increase the height. Okay. So see how we're increasing the height of this? Okay. So what we're going to do is we're going to increase the height. We're going to put a ball in here, and this is just another way of transferring energy, right? So when we put a ball in here, this is going to come down, right?
Yeah. This is also kind
And then it's the same concept. It's the same. It's just different. It's just kind of cool. Okay, so I'm gonna need us to move again, so we don't hurt ourselves. We have the ball. Okay. So this one's pretty fun if it works. So what you have to do, basically, is just so you guys, if you ever want to build this, I built this when I was in high school. We did like get an exact distance, which is pretty fun. But how it works basically is, let's see if we can get this to, let me just get this to attach. Okay. Cool. Okay, you're good. You don't need to hold it. So what's going to happen is when I release this, okay, the weight's going to come down. And then, oh, thank you. Just pull this tighter. Is that better? Okay, great. So basically what's going to happen is the weight's going to come down, and then this, since there's a string that's attached here, it's going to carry it around, and then the string's going to release. And it's going to have a huge arc. And so it should go further. But we'll see. Does anybody want to pull it? Okay, you want to pull it? Okay, so all you need to do with the string, just pull it when I say go, okay? Yeah. Yeah. All right, you good? Whenever you want, you can pull it. So it had a higher arc, but it went about the same. But so, what's the main idea here, guys? Thank you. Yeah,
to see the potential kinetic energy.
exactly. And so, can anybody tell me then how this works in the zip line? Yeah.
When you let go, it goes straight down. So
Right.
it's kinetic energy.
It's kinetic energy down, yeah. But what else is going on?
When it's up high before you release it, it has a lot of potential energy, and then it goes to kinetic as soon as you release it.
Exactly. So that's the whole point of showing these things, right? Is that these do the same thing, right? They store potential energy. So when you hold it high before you release it, and then once it goes down, it goes all to kinetic energy. Okay, so we're gonna go sit back down, and then we're gonna. Cool. Good job.
She said they defeated on the velocity equation later on.
That's X over 2.
I know. All right, here's a question. And can anybody think about, so does anybody know what forces act on the zip line, on your little carrier? Can anybody name a force? It's okay if you can't. We'll go through it too. I'm just curious. Anybody know? What keeps us on the ground? Yeah? Gravity. Okay. And then, let's see. Can anybody think of something that would, can anybody think of something that would make the carrier not want to go forward? Yeah? Magnetism would, but I don't think there's any magnetism in the line. Yep. Air resistance, or think of it as wind. Yep. Wind, right? Anything else? Friction. Great. So all these things act on it. So do you think that friction and wind help conserve energy? Any idea? Any idea, guys? What did you say? Oh, what I was saying is, do you think that friction and wind or air resistance, do you think that they help conserve energy? No? What about you guys? Do you guys think that? You think it helps conserve energy? No? All right, well, it actually, correct. So it doesn't. It actually it hurts us, right? Because, well, it depends what you want to do, but, yeah?
Because it pulls you back, because you want your car to go forward in the zip line, and it's going to pull you back.
Right, exactly. So it's gonna stop, it's gonna take away some of that energy when you're converting to potential kinetics, so it's gonna slow you down, right? That's why you get slowed down. So, let's see, we have some cool pictures here. So if you think about a skydiver, right? I don't know if you guys have ever been skydiving. I'm not going to do that. It's too scary. But, you know, skydivers, they go like this, right? They have their whole body down. And that's because they want to slow themselves down. If they were just to go straight down, like if you can imagine that, they go a lot faster. And we'll explain that in a little bit. And the same thing with friction, right? So if you're going forward, friction is going to oppose your motion. So I'm in a... I don't have something to show you. Okay, so if I have this block here, right? Which way is friction going to act if I push it this way? Which way? You guys can just shout it out. Right. And that's why it slows it down, right? It slows it down because it's friction this way. There's no friction, it would go on forever. Like think about it on an ice rink. You know, it would just go forever. Okay, so we are going to draw a quick free body diagram. I don't know if you guys need to learn about these yet, but what we're going to do is we're going to have our carrier here. Okay, and it has some mass or weight. Okay, so can anybody tell me what forces are on here? And we kind of just listed them, but in which directions? You can tell. Yep. Down for what? Right, so gravity's down, right? Is that what you're saying? Yeah. Cool. Right, so down is, I'm going to do gravity as a capital G, okay? All right, any other forces that we have on here? Yep. Friction. Now, let's say we're going this way. So this is our motion. Which way is friction? To the left. Okay, cool. Okay, any other forces on here? You guys have some other. What force did you guys talk about? You guys say wind? Okay, which way do you think it's going to go? What did you say? Let's say the wind always goes against the... Let's say the wind is trying to slow you down. It would be going up. Gravity is trying to pull it down. Yeah, what are you thinking? If you're going to the left, right. And you are right, actually, but because we're not looking at it at an angle and we're looking at it horizontally, it's going to be opposing the motion to the left. But there would be, I can talk to you later about that. That's definitely something. That's correct. Okay, and there's actually one more force on here that I'm not sure if you guys have learned about yet. And we'll do the W for wind. Yeah. No, we'll actually get to that later. There's something that's happening here that since gravity is acting down, there's something that has to oppose it, or else this thing would just go through the ground. And that wouldn't be good. So there's actually a force that acts upward. What? There is lift, but we're not accounting for that. It's actually called a normal force. I don't know if you guys have heard of this before, but all a normal force does is it opposes the gravity. So it allows your object to stay on the zip line. So this is a free body diagram. We also have it on the slides. And the directions, I guess, are opposite. That's okay. So again, we have gravity acting on it, normal force that opposes the gravity, and then wind and friction. So these are your main forces that are on your ping pong holder as it comes down. So I have a question for you guys. What force is responsible for actually driving or actually making your mechanism or making your holder move? Like what force causes it to move? Yeah. Oh. Let's see. Let's get somebody new. Who hasn't done it yet? Let's see. You have. Anybody new? Okay, fine. Who's gone? All right. Yep. Right. Exactly. So I just want you to remember this. Gravity is the main force. It's the force that's acting that causes your object to want to go down. Because if you think about the what actually causes potential energy is your weight, so it's your mass, times gravity, times the change in height. So gravity actually causes you to have energy, and then when it's released, the gravity will actually cause it to go down. So that's kind of an important thing. So now I want to ask you some questions about air resistance or wind. We say wind or air resistance is the same thing, but so that you don't get so confused, you guys don't get confused. I don't mean wind like you feel outside, like when it's blowing at you. I mean just think about there's air there. It's not like it's actually blowing. It's like you're going into it. If you think about, have you guys ever been on a boat? Do you guys feel that when you're on the boat and it just gets really windy all of a sudden? Why is that? Do you guys know? Yeah. Right, it's going really fast. So you're hitting the air. It's not like the air's blowing on you, right? So think about it that way as opposed to there being a wind force or something coming. Okay, so cups or these things, I guess. Let me get one. So you have your little holders or whatever you're going to make, right? What do you think contributes to the air resistance on this thing? What do you think changes it? Yeah. Wider. Okay, so like the area. Yeah, what else? The surface area. Yeah. Yeah. The weight. Okay. Anything else? Great. Okay. So we're going to try to do some experiments here to see how changing what word did you say again? Surface area. So how changing the surface area. So the surface area is how much space there is here going down when you face. So when you're going down the zip line, like how much contact space there is here that's opposing the wind. So we're going to do some experiments to change the surface area and see how that affects our little carrier. So we're going to go over the zip line. So you guys can come with me. Nine seconds. So do we think, let's do that big one there. Yep. Do you think that one's going to take longer or shorter than 1.9 seconds? Longer, shorter? Wow, okay, we're not in agreement here. So let's see what happens. Okay. No, they all weigh the same. They all have like one little thing inside. Are you guys ready? Here, be careful, I'm gonna hit you. There you go. Okay. That took. How long do you think it took? 3 seconds. Right, that was 3 seconds. Okay. So 3.1. But yeah. Okay. So what about this one? Yeah. What do you think? Pretty slow. Let's try it. All right. So we think it's going to be the same or faster or slower? Let's see what happens. Let's see what happens. Okay. So that went about 2.1 seconds. So that was in the middle actually. So what do we learn from this? Yeah. It depends. Exactly. Yep. Right. Exactly. And we'll get to you in 1 second. Okay, cool, good. So you can change how fast your holder goes down by changing the surface area. So what we learn from this is that the larger the surface area, the slower it should go. Okay? But then we have another question for you, and this is going to bring up our next topic is, what happens if you change the mass? Will that make it go faster or slower? Faster? 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 Okay. So we're going to quickly go back to the screen so we can do a couple slides on this, and then we're going to come back here and test it with different masses. Because I'm not sure, maybe it'll go faster or slower, maybe it'll stay the same. But let's figure that out, okay? So what were we thinking? We were thinking that if we add more mass, or add more, you can think of it as weight, if we add more something that's heavier, is that going to make it go faster or slower? Yep. We're always going to be going down. Right, and so it's going to go faster, you think? Okay. Mhm. Okay. What about you? Okay. Well, we're gonna test our ideas out. We're gonna see what's happening. Oh, just automatically change. Oh, you did it. Thanks. Okay, so does anybody know about the Newton's laws of motion? Anybody heard of those? Yeah? Right. Exactly. And so what really, we don't really need this, but it's just something that you guys could think about, is that if you have a heavier object, you need a larger force to accelerate at the same rate. So if you have a really small ping pong ball, okay, and you want it to get to a certain speed, or you have a really big bowling ball, okay, which one do you have to put more force on to get to go the same speed? Which one? Bowling ball, right. So this is going to bring us to our topic of changing the mass. So what we have here is we have blocks of the same size. Okay? We have a bunch of them. And why is it important that they're the same size for us to test this? Yeah. They're not the same mass, but do you know why it's important they're the same size? Same surface area, right. So, because we just showed that when we change the surface area, we change the speed, right? So, we're going to test and see which one's faster with mass, right? We want to make sure that we're holding things constant. And so, we're going to just change the mass. So, this one has, you guys familiar with grams? You guys do that in school? You use grams? Yep, so we have 105 grams here and 61. We have different weights and different sizes. So, now what we're going to do is see what happens when we change the mass, keep the surface area the same, and see how that actually affects us going on the zip line. And you guys think, and I guess so do I, that it's going to change, right? So we think that the heavier object is going to go faster, right? Well, let's test it out. Let's go back over here. Great. Okay, cool. So whatever one you want to start with, that's all you do. Can you give them the mic so that they can hear me? Is it on? Is it pushed up?
Hello?
Yeah, cool.
So we talked about area, right? Surface area, size being.
Just hold the shoe like that.
Oh,
There
sorry. So size is important. If all these are the same size, then we would think that a different mass would make it travel down at a different speed. So we have a 47 gram weight, a 78 gram weight, and a 24 gram weight. Who thinks which one is going to go faster down the zip line? All right, go for it.
So what you're saying, right, is you're going to say that, so when this weight's on here, it's going to pull down a little bit, and so it would have less friction, right, than this one, which is going to pull down a lot more, right? That's what you're thinking? Okay. 78.
Okay, so we think that heavier weight is going to go down faster?
Yeah.
All right, let's test it.
Yeah,
That's mine. Yeah.
Oops.
you can pick that up. Yeah, just don't get it on each other,
Another part.
We wouldn't want anybody to be messy. Okay. So we're going to start with the 24 one. Okay, so we're going to look at the time for you guys. If you want to start it like right here, that's actually what they do in the competition. All right. Cool. So that one goes.
1.82.
Wow. Okay. Thanks.
Oh no, go next.
All right, which
We'll
one?
go up.
Which one are you next?
All right, this is the 47.
47
47
grams.
grams.
Wow, we're getting heavier. Okay, what do we think is going to happen? You guys can just shout it out. Slower, faster. Okay, let's see what happens.
It was slower.
Okay, it will 1.76.
1.76.
Pretty constant. Okay, this is the
This is
the
the
heaviest
78.
one.
78.
It's gonna go fast. And it kept
All right, so that went about 1.7.
1.65.
1.65. Okay, so let's try the heavier ones too. We're not sure yet, are we?
Wow, it's because they use the same surface.
That one 1.65.
It's still working.
It's because it has more.
Did change.
1.65. Okay, how much is this one gonna go? That was 105 grams. No, 1.65. Let's see what happens.
Slower. Faster.
Oh, that bounced back, but it was about 1.7. Okay, so now we're really confused, right?
Those had more air resistance to bigger.
Right, exactly. So they had more surface area, correct. But is there really a big difference between something going 1.65 and 1.7?
Yes, there is.
Okay. Well, in our context, it's not actually. So we're going to say that they're pretty similar, and there's going to be some variation along the zip line. There's going to be just difference in contacts and all that stuff, but generally that's about the same. So what I want you guys to know is that the mass actually doesn't really matter, and that's because if we think about our equation, and we didn't really go over this, but is there mass in the equation when you're using potential energy? Yes? Okay, what about kinetic energy? Do you know what the equation is? It's m times v over 2. So there's mass in both equations. And if we're conserving energy, we're setting them equal, so mass drops out. So in any of these zip lines, any of these conservation of energy things, the mass of your object doesn't affect the speed. It shouldn't affect the speed. But there's a catch here. Anybody know what it is? Yeah. Yes, kind of. But the catch is a little bit different. There's still something that's, sorry, one question for you. Is energy conserved on the zip line? Okay, but as it's going down, is it conserved? No, it's not. Energy is being lost, right? So then, would the mass matter? No. So the mass matters actually to a certain point. So we're going to go over this in a little bit. But if your mass isn't high enough to overcome the air resistance, so let's think about it being like super light, like a feather, right? It's not going to be able to go down. But if it's heavy enough to break that air resistance, heavy enough to break that wind, then it's always going to be the same. So it's important for you guys to know, if that makes, and we'll go over this again so it makes more sense. It's important for you guys to know that when your holder's coming down, if it's heavy enough to overcome that air resistance, so it's heavy enough to over and not get out in the wind, right? Then it's not going to matter how much more weight you add because it's going to go the same speed. But if it's too light, then it's going to slow down. And that's because energy isn't conserved here. Okay? Yep.
How do we know if it's able to overcome the wind challenges?
The air resistance?
Yeah.
Well, that's just going to be a trial and error. Yeah.
And if we see this up the way it's positioned, so if you have a position, for example, on two like this, it might go slower or faster. It's like this, it might go faster than this.
Exactly. So what I want you guys to realize is there's a couple of ways to change how fast your holder goes down, right? What are they? Yep.
Changing the surface area.
Surface area, right? So that can make it go slower or faster. Anything else? Yeah. So mass can affect it, right? So what we're saying is that if it's too light, okay, the forces that are opposing it, so the friction and air resistance, are going to really slow it down. But if it's heavy enough to overcome those, then it's not going to matter how much weight you add. So this is a perfect system, and we're going to show a video that's going to show you that. If this is perfect and there was no friction, no air resistance, mass wouldn't matter at all. That's kind of crazy, right? Mass wouldn't matter at all. So what we're going to do now is we're going to go watch a quick little video, okay? We're going to drop a feather and a bowling ball, okay, in a video. We're not doing it here, okay? If we drop a feather in a video, or if we drop a feather and a bowling ball in this room, what's going to happen? Which one's going to fall faster? Bowling ball. Why?
Yeah, but gravity's gonna act. Gravity's not.
Right. Okay. So there's more air resistance on the feather, right? So it's gonna go slower. The bowling ball's gonna go down. What happens if we put them in a vacuum? What if we put them in a place where there's no air resistance? So yeah, let's play. We drop them in space. What's gonna happen? Yeah, you guys can answer. Yeah. Nothing? Okay. Sorry. Let's say there is gravity. There is gravity here.
Wait, so are we on Jupiter?
We're not on Jupiter. So let's say we're on Earth. We're here, but we took all the air resistance out of this room. You guys couldn't breathe. We have a little breathing mess. Okay. So what's going to happen if we drop the bowling ball and the feather in a room where there's no air resistance? They go the same, or are they different? Let's test it out, and then we'll kind of understand more of why the math doesn't matter. So let's come over here. All right, cool. So just so you guys, it's a confusing concept, definitely, that we think that mass actually. So I know you guys think that, okay, 1.65, 1.7, right? And so that actually is faster. But if you saw in the changing the air resistance, one went like 1.5, 1.3.5. So that's the difference that we want to see. A 0.05 second difference is not very, yeah. Right. So because we're just building something, we're not doing anything very precise. This is going to be, we're going to say it's pretty much the same. So like I said, you just want to make sure that your cart or your carrier is heavy enough to overcome the air resistance if you wanted to go faster. If you wanted to go slower, you can make it lighter. And that way, adding more mass after that point won't make a difference. So let's see if this works. It might not, but I hope it does. But anyway, so we have a bowling ball and we have a feather. We drop them normally. What's going to happen? Clank. Okay, what else? Yeah? No? What? Okay. So there's air resistance when we're here. Right? So let's say there is air resistance. Exactly. Okay, and then what happens when we go into a place where there's no air resistance? Which one's going to fall faster? Yeah, so at this point shape doesn't matter, right? Because there's no air resistance. think the bowling ball is going to fall faster? Yes? Right, but there's no air resistance. So what do we say? So remember when the masses went down like really close to each other? The different masses, and they really had almost the same time? You guys remember that? We just did it? Cool. So do we think that it will matter which one's heavier if there's no air resistance? Do we think so? No. So this is kind of just furthering the, it's probably not going to work. That's okay. That if there's no air resistance, they're going to fall exactly the same. Which is kind of crazy. You should watch this when you get home. It's crazy. There's a bowling ball and a feather, and they fall exactly the same with no air resistance. And that's because mass doesn't matter in terms of conservation of energy. The mass of your object doesn't matter. It only matters when there's external forces on it, like wind or friction, which is what you have. But at a certain point, it doesn't matter anymore. So now we're going to learn about something called average velocity. So does anybody know what speed is? Let's see. Let's get somebody else. You're good. You're answering a lot of questions. Anybody over here want to know? Yeah. Any of you guys know what speed are? Let's see. What about you guys back there? You can just tell me anything. It's okay. Okay, let's see. Well, you guys can keep thinking. Okay, what about any guys over here? No? Okay, what else? Yeah.
Like how fast something is going?
Yeah, right. So like how fast something's going. I mean, what?
It's time. It's the distance divided by time.
Yes, that's the equation for it. That's totally correct. I was thinking more like broader picture, but yes, that's very correct. So right, so speed is just kind of distance divided by time. It's how fast you're going. And so what we're going to learn about here is something called average velocity. Now, what's velocity? What's the difference? There's a difference here, actually. Okay, so I have a question for you. Let's say that I'm walking this way, okay? And I have a speed, right? Because I went to distance over a period of time. Oh, you guys said, yep. I just can't hear you. What did you say? Exactly. So did you guys hear that? Probably not. Okay. Velocity is speed and direction. Okay? So it matters which way you're going too. Okay? It's not really a big deal for your zip line because you're all going to go one way. Right? But the velocity you're thinking about it is going down the zip line. Right? Because it's the speed and the direction. So what this is saying is that the average velocity, and in our case I think we can think of it as average speed because we're just going one direction, it's the change in distance. So let's think about, I'm sitting right here and I'm going to walk from that blue line to this blue line. Okay? What's the change in distance? Yeah? From here to here, right? So if I were to measure a distance, it'd be from when I walk from here to here. Now, what's a change in time? Anybody know? That's kind of weird, right? Yeah. Okay. Right, so how long it takes. So with this, when I start here, we think it's going to be the time equals to 10, time equals to 0, time equals to 100. What are we thinking? Yeah. Okay, yeah, so if we said this is time equals to 0, so this is our start time, then any time that it takes to go to here is our end time. So our change time is just our end time. So let's say it's 2 seconds minus 0, which is 2 seconds. So we're going to do a quick example. We're going to do a problem here to try to see if this can make more sense. It will definitely make more sense with the problem. So does everybody have this? Oh, okay, yeah. So I guess so we know. This is average velocity, and it's in units of meters per second. We don't really need to understand that, I don't think, very much. So we can actually skip this. What happened? Oh, okay. Okay, so we have a problem here. Okay. So we have our guy John, and he releases his carrier. He's releasing himself on the zip line, okay? So he's going to travel 2 meters in 10 seconds. What's his average velocity? And so you guys can work on this as a group, and then we'll come around and help you if you need help. Okay, you guys can just shout out the answer if you think you know it.
22.7 per second.
Great. Yeah. Sorry, I gave you a fraction. I didn't think about that. Right. So what did we do here? Okay, we had your average velocity is your change in distance over your change in distance over your change in distance over change in time. Sorry, I just thought the numbers were switched, which was confusing me. So you have 2 meters that you're going, right? So he's going 2 meters. Okay. And it's taking him 10 seconds. So it's 2 meters divided by 10 seconds. That's 0.2 meters per second. So that's just a calculation that you'll probably have to make. I think you do some sort of test or something. So this is something to know for when you do that test. So actually, this is all we have in terms of our lesson. I think we're going to also get time to practice on this. I just wanted to know if anybody has any questions, because this is confusing. Yeah.